Okay, then let's continue with the second problem. So, okay, underline. So the second problem we have the rigid body bar of BDE is supported by the two links AB and CD. So we have this BDE bar, and then we have two support here. I will mark as blue, two support. And then we have the link AB as aluminum. Young modulus is 70 gigapascal, and the cross-section area of it is 500 millimeter square. And we have link CD, which made of steel, and then we have young modulus of 200 gigapascal, and then we have cross-sectional area of 600 millimeter square. And then for the 30 kilonewton force shown, determine the deflections of of B, of D, and of E. What is deflections? Deflection is deformation actually. Okay, so then first what we have to do. So let's get to the problem. So problem 2.1. So the same we did as usual. So normally we will have to find the force from the support, but in this case, since we interested in this bar, written like this, we have this kind of bar, and then we have 30 kilonewton force, and then we have this support. Okay, what we have to find is we would like to find the force. This is the assumption force from the support from the bar itself. Okay, so this is B, D, and E, and then we would like to find F AB and F CD here. Okay, then what we can easily do is what we use sigma F equal to 0 and sigma M equal to 0, so that we can find this forces. Okay, because this is in equilibrium. So let's start with sigma MB equal to 0. So I'm rotated at B. Then we will get minus 30 kilonewtons times 0.6 millimeter plus FCD times 0.2 meters. Then we will have FCD equal to plus 90 kilonewtons as tension. Okay, and then we have this is the force from CD. So what about the force from I will take another moment D at point D. Then we will have 0 equal to, actually you can use also sigma F equal to sigma Fy equal to 0. Maybe I just change it to sigma Fy equal to 0, and then we have FAB, then we have plus 90 kilonewton, and then we have negative 30 kilonewtons equal to 0, then this is resulting in FAB equal to negative 60 kilonewtons in the end. Okay, so means our here is this directions, yeah. All right, so then we would like to find first a displacement of B. So you know the action equal to reaction, so there is another our force will be in the opposite sign, right? Because this is a reaction from the bar. So FAB is equal to 60 kilonewtons. Then we use this formula again. And then this one we have force as 60, negative 60 times 10 to the power of t newtons. We have 0.3 meters. And then we have area of 500 to the power of minus 6, because we need to change the unit to the SI unit, and then our Young modulus is 70 gigapascal. Then we will get the formation of minus 514 times 10 to the power of minus 6 meters. So we have the deformation or displacement of 0.514 meters upward. Okay. Next, B displacement of D. So here again we have the tension in this case. CD equal to 90 kilonewtons, and then here we will have this formula again, but in this case our area and Young modulus and force will be changed, also the length, so everything is changed here. 90 times 10 to the power of minus 3 times 0.4 millimeters, and then this is over 600. Don't forget to change the unit to SI units, which is meters, 200 gigapascal, and then in the end we will have 300 times 10 to the power minus 6 meters. Yeah, so we have the deformations of 0.3 millimeters downward. Okay, so this is our answer for those two. And then C, we would like to know the deformation of this point. Yeah, so point E here. Okay, so the point E is a little bit tricky. We need a little bit knowledge from the triangle rules. So we have this line. If you take a look at the pictures, this is point B, this is point D, isn't it? And this is E. You know already how much each of the bar here, the bar here, how much is deformed, right? How much is expansion and deformations? And actually, this one is compressed. This one is expanded, or this is shrink. So this expanded means in the end we will have something like this in the blue line. This one is expanded, so it's a little bit downward. And you can imagine that our bar is rigid, so means our bars look like this. A little bit exaggerated here. And then you know already that this is 200 millimeters and this is 400 millimeters. Okay, then you know that this one deformed by 0.514, this one deformed by 0.3 millimeters. Okay, so first you have to find this intersection point. So I will define this as x and this is defined as 200 minus x, 200 millimeters minus x. And in this case you know that this angle here, two of them is equal, right? Two of the angle is equal. You use the formula tan theta equal to 0.514 over 200 minus x, and then this one, so we use the same formula here. So tan theta is equal because those angle is equal, so I also use this into this one, so it's equal to 0.3 millimeters over x. And then when you solve x, you will get x equal to 73.7 millimeters. Okay, and then you can also use this kind of things. Now you know x already, so from this you can use some kind of this triangle. You know, angle this is x is 73.7, this is 400 millimeters. You know tan theta again, this one you know that this is 0.3, this one you as a lambda e here. So for this tan is equal to 0.3 over 73.7 equal to this one over 400, and then in the end our deformation is equal to 1.928 millimeters down. Okay, so then we can answer all of them. Okay, so next is the thermal stress. So regarding the thermal stress, this is, as I explained it in some class before, the thermal stress is, for example, if I just put on example, when we have a bridge, no, maybe I would just say when the temperatures change, the material is try to expanding or shrinking depending on the temperature change. Yeah, that is also the formula for thermal expansion coefficients. And this, the temperature change resulting in the change of the length or a thermal strain. There is no stress associated with the thermal strain unless the elongate is restrained by the support. So if, for example, in this case, picture A here, you didn't fix the end support. When the temperature is changed and is governing by these equations, so when there is a temperature change delta T, and then the length multiplied by the length, and this is thermal expansion coefficient, you will get these deformations. Means when you have the change of the materials, the temperatures, then the material tries to expanding or shrinking. Okay. Then if you didn't have any fixed end here, then there's no stress. It's just expanding without any stress. Yeah. But if you put the restriction here, then it's try to expanding, and that is cannot expand. What does it mean? That is, there will be induced the stress inside there, and also the deformation, thermal deformation, and the deformation from the reduction of the support will be compatible. So you have to do the calculation for both the deformation from the temperatures and also deformation from the force. Yeah. Okay. And Poisson ratio. This is really important topics. When you have expanding some things, for example, you expand it here in this p-axis, and then you know when you're expanding, your volume will be the same. Most likely, maybe it's a little bit bigger, the volume, because your molecule is tied to expanding. But actually, when you spread it in, make a tension like this, your length here will be increased. You can see it's increased, right? This original one, and then it's increased by this deflections. But you can see that the other axis here is shrink, because the volume of these materials have to be quite similar to the origins. Means if you expand on the one side, on the other two sides will be shrinking, and then there is the coefficient which defining this. Okay. So in this things, the deformations, for example, the deformation on the x-axis is equal to this formula, stress over the Young modulus, but the deformation on the z and the y-axis is not governing by this equation anymore, and it's not equal to each other's. So the ratio of the deformation of this strain on y and z is called Poisson ratio. Means, for example, if Poisson ratio is 0.4, the meaning is when this one is expanding by 10%, the other directions, for example, Poisson ratio on the y-axis, this one will shrink by 10% times 0.4, means equal to 4%, meaning that the other direction will shrink by 4%. Yeah, and on the z-axis, if y is equal to 0.4, but if z is equal to 0.1, means in the actually this is z-axis is shrinked by 1% because it's 10% times by 0.1, but this one in shrinking in y-axis is by 4%, for example. Yeah. So here is the generalized for the Hooke's law. In the Hooke's law, for example, if we have material s square like this, we define the geometry as 1, 1, and 1 to be more understandable. And the deformation of its and on the x-axis will equal to this. This is normal expansion on, sorry, let me erasing this. This is normal expansion by x-axis here. Okay, and this is also normal expansion by y-axis. This is normal expansion by z-axis, and these things is where is the Poisson ratio play a role. When you expand it on y and z, you will shrink onto x-axis. Same goes for the y-axis. If you expanding by x and z-axis, it will shrinking the y-axis also. Okay, so this is what we call Poisson ratio, which is applied on the Hooke's law. And this is bulk modulus. To put it more simply, the bulk modulus means we have hydrostatic pressures. Just thinking that you are sinking in the very deep, this is the sea. Yeah? In very deep sea, you know that there will be a lot of pressure, ton of pressure under the waters. Yeah? And this is equal into every directions. And if it equal in every direction, we call it hydrostatic pressures. Means we have everything's equal on all the side, and then you can, from that you can simplify the formula to get the elements of hydrostatic pressure at this formula. Yeah, just for you to know about it. Okay, and shear strength. So this one is quite similar to the Young modulus. Okay, this is normally Young modulus is just the expansion when we have the normal force when we expand it on one direction, but this one is the shear strength. So how it deform in shear. So this cubic is subjected to shear stress, and it will deform rhomboid like this, become like this, like a diamond shape, and the corresponding shear strength is quantified in terms of the change in the angle. So it's will defined by the angles, and then we call this one is modulus of rigidity or shear modulus. How much it deformed by the shear stress. Okay, so let's stop